Gravitational fields. A gravitational field exists in space surrounding an object in which the force of gravity is exerted on objects. So it doesn't matter if the object's small like my pen or giant like the Earth. Now what we also know, I don't know if you can see it, are these little arrows. So close to the Earth, the gravitational field strength is significantly stronger. As we move further away, it gets smaller, and then here we see it's smaller still. So as you get further away from an object, that gravitational field strength actually decreases. That's our little g. So we have this formula. So we know the force of gravity is equal to capital G, which is 6.67 times 10 negative 11 Newton meters squared per kilogram squared. Mass of the first object times mass of the second object divided by the distances squared. And that's from center of the one object to center of the other object. So if you're dealing with really large objects like the Earth, you can't do it from the surface of the Earth. It's from the center of the Earth. So sometimes we have to add in the radius of the Earth. We also know from Newton's second law, we have another force of gravity formula, which is just simply mg. And essentially, these two are solving the exact same thing. They're both solving the gravitational force of an object. If you know the little g, you can use this simple, small formula. If you don't know little g, and we do know it on Earth, which is 9.8, what we have to use is this bigger formula. This is a universal one that works anywhere in the universe. So because the two actually solve for the exact same thing, we can set them equal to each other. So when we do that, you have mg is equal to the gravitational field strength, that universal gravitation, capital G, m1, m2 divided by r squared. The little m's cancel out, and we have a formula to solve for little g. Determine the mass of the Earth using the magnitude of the gravitational field strength. Well, we're looking for m. That's mass of the Earth, so it's capital M. The capital is always denoted by the larger object. The gravitational field strength, we know what that is. That's just little g. So little g is 9.8 newtons per kilogram. That's pretty easy to figure out. All you have to do is hold up a Newton scale, put a 1 kilogram mass on it, and the needle will actually read at 9.8 or close to 10. The distance r between Earth's surface and its center is 6.38 times 10 to the 6. So we know what r is. That's in meters. And we know what the universal gravitational constant is. That's our capital G. That is 6.67 times 10 negative 11 Newton meters squared per kilogram squared. Well, my new little formula for G is capital G, capital M divided by r squared. But I'm trying to get m all by itself. So first thing I'm going to do is multiply both sides by r squared. And then I end up with gr squared is equal to capital G m. I'm trying to get it as m all by itself, so now I'm going to divide both sides by g. The g's now cancel. And my formula for m is this. M is equal to little g r squared divided by capital G. So we plug in what we know. Little g is 9.8. The radius of the Earth is 6.38 times 10 to the 6. Don't forget to square it. It's the biggest mistake if students forget to square it. Divide by capital G, which is 6.67 times 10 to the negative 11. When you put all of that into your calculator, you get 5.98 times 10 to the 24 kilograms. So we're able actually to calculate the mass of the Earth using this formula.